everybody. Welcome to the St. Louis Angular Lunch, sponsored by Oasis Digital, who's provided the space and the pizza and the ambiance that you're enjoying. Today we've got a presentation from Andrew Wiens, who is a developer, consultant, raconteur, man about town for Oasis Digital on machine learning for front-end features. Once Andrew's given the presentation, we'll do Q&A at the end, unless you want to take questions along the way. How would you prefer to do
that? Questions along the way is probably fine.
Okay, so questions along the way as long as they're nice and relevant. Again, this is sponsored by Oasis Digital, so let's see, I was asked to gently plug Oasis Digital. Oasis Digital, software development consulting firm, also the people behind Angular Bootcamp and quite a lot of other training that's currently going on right now. So make sure you check out oasisdigital.com, especially the training section where there's a lot of new stuff that's showing up. But also if you have software development needs, architectural consulting, really anything to do with large-scale front-end web development or even full-stack development at this point, definitely take a look and talk to the folks at Oasis. Otherwise, Andrew, take it away.
All right, so thank you all for coming. As Bill said, this will be a talk about machine learning. So the goal for this talk is to show sort of what's possible with machine learning in JavaScript, as of 2019 now. It's come a long way in the last few years, particularly the last year. And I'm going to focus on the TensorFlow.js framework. So just as an overview, first I'll introduce my talk a little bit and my own personal background. Then we'll get into the TensorFlow framework, as well as the JavaScript version. And I will also go through a few ideas that I just came up with for features that you could use with TensorFlow.js and Angular apps. Then I will go through a few concepts that are relevant to the demos, and then I'll show two demos at the end using TensorFlow.js with Angular and Node.js. So first of all, I wanted to address the question that everybody asks when they first start learning about machine learning. What is machine learning and how does it compare to artificial intelligence? So there's people that are somewhat opinionated about there being a difference between these two that's very clear. If you go to Wikipedia, these are the definitions that it gives. So artificial intelligence, using computers to mimic the cognitive functions of humans, and machine learning, perform a specific task without using explicit instructions. And to me, these two it's not very clear what exactly the difference is. And the reason for that is, as Larry Tesler pointed out, who's a computer science veteran, that artificial intelligence is generally used to mean whatever hasn't been done yet. So by definition, then this talk is going to be on machine learning, since it'll be on things that we know how to do. So some of my own personal experience with machine learning, I am an Angular developer right now, and Node as well. But I don't day-to-day do machine learning. In graduate school, I did some projects related to machine learning. One of them was directly machine learning. The other one was signal processing, which is a lot of related math and concepts, not exactly the same thing. So on the left is my project that I did with signal processing. This was trying to measure the timing of heart events using wearable devices, specifically accelerometers and gyroscopes in those devices. So the graphs here in the middle, this is a raw waveform from a wristwatch accelerometer. And so this is essentially the vibration signal that you can record at the wrist when you're standing still. So if a person is just standing there and you take several heartbeats from the accelerometer, this is kind of what you get. If you filter this, so this is around 2 hertz to 20 hertz, something like that. It's a relatively wide band filter. If you choose the maximum point, you can correlate this pretty well to when the heart valve opens, the aortic valve. what I found was that if you train a filter on a specific person, so if you have them stand still while they're recovering from exercise, their different cardiac parameters are changing quite a bit, so you get a nice dynamic range. Once you train it, then you can get both the opening of the aortic valve and the closing. So I did a bunch of work on this. The details of how you train the filter and how filters work in general uses convolution, since it's a finite impulse response filter, and that's the basis of a lot of convolutional neural network architectures. I also did a project on bioinformatics. So in bioinformatics, there's a problem that people have solved where proteins will bind to DNA depending on what the specific combination of base pairs or letters is. So in DNA, you have 4 different possibilities at each DNA spot in the DNA. And they have what's called motifs. So this is showing that the relative height within one of the base pairs shows what proportion of the time this particular protein binds. So if there's an A here, it's much more likely to bind than if there's a G. And the height relative to between the pairs shows how much information they tell you. So if you have a G here, it doesn't tell you very much about whether the protein will bind compared to if you have a T at location 4. And so I did some work with convolutional neural networks and recurrent neural networks and maybe one other. I was basically implementing other people's papers and seeing how they worked in TensorFlow. This was back when TensorFlow first came out. So it was I used it as an opportunity to sort of learn about the framework and get into machine learning a bit. So with that, I'll jump right into TensorFlow.js. So first of all, what is TensorFlow? This is Google's framework for machine learning and artificial intelligence. It's for Python, so usually people have their own local setup with Anaconda and Jupyter notebooks. And they usually use an abstraction layer like Keras. This is on top of TensorFlow and abstracts a lot of things that you use with deep learning, different types of layers that you can use. It gives a lot of things in the box. But you can often, if you really wanted to, you could do a lot of things just straight in TensorFlow. And so a few years after TensorFlow came out, they came out with TensorFlow.js, since there was a lot of interest in JavaScript-based machine learning. There's a lot of JavaScript developers, obviously, and if you want to incorporate it into your application, if there's a JavaScript version, that's a lot more straightforward. So this is available as several NPM packages, so it's just an NPM install away from being used, and it works in either Node or in the browser. And these are just the capabilities that they list. So you can, in your browser or in Node, you can create models, you can use pre-trained models, so models that other people have trained, or you can retrain imported models. This is often called transfer learning. And so they have a page full of demos, and I'll just show that real quick. They have a bunch of different examples. A lot of these are broken. It might be related to the fact that 1.0 just came out. I'm not sure, but they have a whole bunch of examples. I know that the cart poll is working. So if I go here, this is kind of a classic machine learning, and it even predates what we now call machine learning. This is a problem where you try to have the machine learn how to balance a rigid object without knowing any of the physics. So you just have it try different iterations until it gets better and better at balancing the pole. So they have a whole bunch of these, and this is all happening right in the browser. So a brief history of TensorFlow and TensorFlow.js. As I mentioned, TensorFlow came out a little while ago, November 2015. Another group created what's called Deep-Learn.js in 2017, and this was extremely popular. Apparently, like this is a really like in the front-end machine learning community, this is really well-known example. It predates Deep-Learn.js by a little bit, but this was like an online playground where you can play around with deep learning in the browser. And this was so popular that apparently it inspired them to create Deep-Learn.js as a package for doing deep learning in the browser. This actually became TensorFlow.js core. And so when TensorFlow.js came out in 2018, that became part of that project. And then, as I mentioned, 1.0 just came out last week. So now we have the first major version of TensorFlow.js. There are a few small breaking changes, but the main change was performance. So as we can see here, there's, in the case of the iPhone X, drastic improvement. I was a little bit sad about this. I just got a Pixel device myself. But these were, this was apparently the big improvement with 1.0. So the different parts of TensorFlow.js, there's the core part. This is the low-level API, which came from Deep-Learn.js. This is essentially the same functionality as TensorFlow proper, so the Python version. There's a TensorFlow.js layers package, and this is their API that's similar to KNearest. So rather than waiting for another package to come along like KNearest, they, I guess, just built their own, which is really nice. There's also a converter. So if you have existing models from the community that's using TensorFlow or Keras, you can import them pretty easily with that. And so if you import at TensorFlow/TFJS, this will bring in all three of these packages. TFJS itself, this package works in either the browser or Node. If you want to have some performance improvements for Node, they have two packages for that. One is using the CPU, and it leverages C++ bindings for speed improvements. The other one is using the GPU. And so for that, you have to have a CUDA compatible graphics card from NVIDIA, and you have to be using Linux. This is really essential if you're going to do deep learning, if you're going to train deep learning networks, since at least large deep learning networks, since the training is very compute heavy. But if you're just doing inference, so if you have a trained deep learning model, even if it's quite complex, they're generally not nearly as bad for requiring compute power, and then you don't need a GPU necessarily. And then the other part that's really great, and I'm going to focus on this a lot, is they have these pre-made models that they've been releasing under the @TensorFlow models namespace. And these are extremely handy, and most of these came out in the last 12 months. So these are some of the official models that they've released, and I have the age of these packages here, so the first time they were released. So 10 months ago, they were released in a trained MobileNet. So MobileNet is, it's actually a family of architectures for identifying objects and images. Google had a big part in MobileNet. The reason why it's called mobile is both because it's trained on things that you would typically take a photo of with your phone when you're out and about, and also because networks are supposed to be computationally sensitive in terms of when you do inference with them, they should be able to be run on a phone and not require some big GPU or something. So this is really nice. They have a KNN classifier, and I'll talk about KNearest Neighbors later. But this is a nice way to, if you have a data set and you have different categories and you want the software to automatically label what new examples, what it thinks new examples are, which category they are, KNN is great for that. And that's a classic machine learning, not deep learning, but machine learning approach. There's also this package called Coco SSD, which will find where objects are located in an image. Their examples are like not, I don't know if it does or doesn't work on like actual images, but they were like images of a triangle or a square, rectangle, that kind of thing. But it might be more than that. I just haven't looked into that. They released within the last month this universal sentence encoder, and this is really nice. I'll show this in the first demo. It basically takes any sentence, or I think text in general actually, and it gives you a 512 length array, so 512 dimension embedding is what they call it. And you can use this as a pre-processing step to do machine learning on natural language. So if you have your own kind of classifier, or if you use KNN, for example, you can convert your sentence into something that you can process, because it will give you the actual tensor representation of the sentence. And I'll go into a little bit more of that later as well. They also have this toxicity package. This one's really recent, 18 days old, well, at least when I made the slide. And that's supposed to tell you whether or not text contains toxic content. This would probably be pretty nice, like just to drop into an application. You wouldn't really even have to do much more with it. Just like to do a front end like blocking of like any kind of bad language. Another one that's available, these are some tools actually, so these aren't models now. TFJS Viz, this gives you visualization tools that you can use. So graphs is one of them. This is an example of what it gives you in the box. I think this is really cool. So it's like, well, what's the point of this? We have chart.js, we have NGX charts. Well, when I've used them in the past, like it's been really easy to do things like this, like to have a coding bug that results in a graph that just doesn't make sense. And you know, maybe they've gotten better since I've used them. This was about a year ago. But to me, like in terms of like data sensitive, like getting the data right on the screen perspective, it should really not let you like give it data that results in something like this. Like this is just, if it doesn't break when you're compiling, and this happens at runtime, like if you get your data wrong and it doesn't happen to be that your years are out of order, it would still look correct, but it wouldn't actually be right. So I think this is something really cool I wanted to look into in terms of just using a graph in a general application, not even for machine learning. So there's also a package for what's called tsne. So tsne is a way to separate high dimensional data to reduce it to 2 dimensions, and also to try to group similar data together. So for example, if you had like the universal sentence encoder from before, which gives you 512 length arrays, you can use tsne to reduce that to 2 dimensions, and then you can plot it. So this isn't using this exact package. This is another implementation of tsne, but this is what it will give you. So in this example, on the left is PCA. Now this is a more traditional algorithm that's essentially comes from first principles of linear algebra. It's how everybody used to do this kind of grouping of high dimensional data and reducing it to 2 dimensions. Often you'll get something that looks like this. Now it kind of is separated, so that like all the 8s are generally up here, most of the 0s are over here, but it's not really that well separated. It's pretty obvious to people, like if you just give an instance of someone's hand-drawn 0 or someone's hand-drawn 8, that those are very different. So we can probably do better, and indeed we can. Several years ago, I don't remember who, but they released tsne, and this is an iterative algorithm that tries to reduce the dimensions to 2 and also tries to essentially push dissimilar examples apart while also trying to keep similar ones together. So it's a pretty general algorithm that you can use on many different kinds of data. It's a very nice way to do visualization. And so this is now in the box with TensorFlow.js, 9 months old. It's another thing to consider if you want to do just general purpose visualization stuff. So I also came up with a few feature ideas for like general front-end applications. This is just stuff that, when I was doing this talk, I was trying to brainstorm different things you could use TensorFlow.js for. So the first one I came up with was image classification with mobile nets. You could combine mobile nets with KNearest classifier. This is actually my second demo. Does something like this. The idea here is you could automatically assign categories, labels, or metadata to user uploaded images. So rather than, if someone hasn't like chosen a category for an image or something they just uploaded, you could automatically sort them to different categories and leverage that to have less of a manual interface. And another idea, I haven't looked into this, but you can flag low quality user content for manual review. So like if you had some kind of listing site, if someone uploaded some images and they accidentally uploaded the wrong ones, it's like a picture of their cat or something when it's supposed to be a picture of a house on a real estate website. You could flag that and have like someone at your company review those, or you could just send a notice to the user, hey, I noticed that your photo probably doesn't contain a house. Are you sure this is a good photo? It was just something that you could probably use mobile nets to do. Another idea was to do sentiment analysis and combine that with Angular reactive forms. I don't know if I mentioned, this isn't a built-in model. This is one of the examples from the examples page that I showed. There's a sentiment analysis example where you basically can type in any words and it will guess whether it's a positive tone or a negative tone. And you could combine that with the toxicity model to like either reject bad language or show users whether a tone is positive or negative. So I was thinking more in the case of like an enterprise application where you're trying to like encourage people to like be positive when they're interacting with clients or something like that. If your application is like that kind of application. Another idea was to automatically categorize the data that's entered in grids or forms. This one's getting more into like doing your own kind of models, because if you just throw like some data at a machine learning algorithm, you're not really, unless you really do a lot of work, you're not always really guaranteed to get good results doing this. But the idea was that if you have some raw data, you could do some machine learning with TensorFlow.js to like give suggested values when people are entering numbers into a data grid or something like that, and base it on the other records in the database. So like if different values are related to various other values, you could like predict what they might be and then suggest to the user to enter that value. You could also leverage the sentence encoder to classify natural language. So if people were entering, text like English words into an input in a data grid or form. And then my last idea here was, that was what I was mentioning up here. So the thing to keep in mind with this is if you do base your algorithm on other things in your database, it's not going to be totally private anymore, especially if you use models that are not like regression or something, but they're actually taking the closest instance in your database, then you actually be exposing like data from your database in that case. So just a warning. All right. So this, I don't mean in this slide to be like really negative about machine learning or to be discouraging of like just trying things and seeing what happens. Just kind of a warning about like, time investment going down different paths. So the idea here is that like with a lot of problems in machine learning that have been solved and that you can now get like an off-the-shelf package to do, it makes it look like, hey, you can just throw things at machine learning and you'll get good results. And that's true sometimes, and other times it's not true. And a lot of people the last several years have spent just enormous amounts of effort trying to get things to work, and a lot of them like haven't succeeded. And so it's just something to keep in mind if you like go headfirst into machine learning, that it can be incredibly it can be frustrating. So like the happy path, and this might be somewhat obvious or something, but it's worth saying that if you have a problem that resembles one that's already been solved with machine learning, you're probably on the happy path still. And then if you have either a pre-trained model that you can just apply to it, or you can do transfer learning, so you can continue to train it both with your own data so that it's refining itself on your new data, that's a very good thing. If you don't have this, then you're going to need something like this, like time and a good understanding of machine learning and enough compute power, lots of clean labeled data that covers all scenarios. So you have to check a lot of boxes. The more things that you need to do that doesn't match what's just off the shelf. And that's true of like anything in software development, but I think it's like an order of magnitude more in machine learning. Like the more different your data or situation is from how the off-the-shelf things work, like it just multiplies the amount of effort that you have to do. Again, not to be discouraging or anything, just to be realistic. So in that vein, I highly recommend trying simple approaches first if the goal is to like get a really good working system. If your goal is to just like learn machine learning and to try it, then absolutely. But like if you're trying to like, deliver something that works pretty well, I would definitely recommend trying things like regression first. Regression often works like really well in situations that you might not even think it would. So there's linear regression. This is when you have like data points and you're trying to fit a line to them. You can also extend that to more than just an input and an output, so you can have multiple variables, and that's what this is. This is linear regression with several variables. So with any two of these quantities, the relationship isn't really that linear, but with all three of them, it is very linear. So like in the sense of, the expected miles per gallon for a car, if you just have that, the miles per gallon and the weight, if you have a lightweight car, you might just expect that it would automatically have a high MPG. But if it's underpowered, then you can see that there's some spread here that's based on how much horsepower it has, things like that. So I'll have to say that if you have continuous quantities and you have several dimensions and you want to predict some other quantity that's based on those, linear regression is great. Ridge regression is a way to use linear regression that's not well formed. So if you have like a whole bunch of input dimensions, so if you had like horsepower, weights, MPG, and then like 10 or 20 other variables, if you use linear regression just straight up, you can what's called overfitting of your data. And so ridge regression gives you a input variable that you can tweak to change how much overfitting versus underfitting the regression does. So this is pretty much related to linear regression. Logistic regression, that will fit a logistic function rather than a linear one. So I don't have an example, but here we're fitting a linear function. Logistic regression will fit functions like this. And this is really useful when you have categorical data. So if you have data that's like either true or false, or 0 or 1, logistic regression will fit a function to that, and it'll let you do regression on categories. So this is really commonly used for classification. So if you have some data and you want to automatically classify them, you can use logistic regression with a threshold. So if it's above 0.5, for example, it'll be one label. If it's below 0.5, it'll be the other. And so I also wanted to point out that machine learning is an automation. It's automating the task of figuring out what your data, what the relationships in your data are, and how you can make sense of it, make predictions from it. So like any automation, it's a solution to problems of scale. So if your problem isn't a scaling problem, you might want to like reconsider whether you need machine learning necessarily. And I'm coming at this from the perspective of like you have to train your algorithm or come up with your own architecture, things like that. If you can just take something off the shelf and use it, then like the time spent developing the thing and the cost and everything is not as much of an issue. But so like in these examples, machine learning was a huge success in chess and Go because these games are computationally intractable in the sense of figuring out exactly what to do at each move. If you calculate all the possible moves for the rest of the game, your search space is just gigantic. So any kind of solution for these games, and especially Go, because it's way more complicated in terms of all the combinations of moves, you have to rely on heuristics. And so classically that meant like handcrafting heuristics for these algorithms, which doesn't scale well because if you're if you're doing it by hand, you're limited by how fast a human can think. And so machine learning was leveraged to essentially automatically learn these heuristics from just playing these games over and over again. And examples of where machine learning was used because the problem was so highly complex or nuanced, vision, just the amount of data in an image is very, very high. And if you have a whole corpus of images and you need to train on that, the data sets are just huge. So machine learning was used in that sense. And also the fact that like it's the relationships between pixels and what they represent is something that we as humans, we can just look at something and get it really quickly. But training a machine to learn that is a very complex task. So deep learning, convolutional neural networks, those were used to great effect in vision because the task was just so complex, the relationship between pixels and what they represent. Speech is similar. There are people that spent like decades, like their entire career essentially, developing speech recognition algorithms. And then deep learning came along and within like a couple years had like completely made all those obsolete. So the problem of like, as humans we can just hear someone talk and understand what they're saying, but how to make a machine learn how to do that, again, is something that's so complex and nuanced that when you set it up correctly with machine learning, the machine can learn it much better than a human can like craft all the corner cases and come up with algorithms that fit the problem. Music and art are similar. What makes good art? How do you take a style? There are a lot of style transfer algorithms out there now, so if you just give an input image and you give it a second image, it can apply the style from the first one to the second one. So you can make like a photograph look like a painting by a certain kind of painter. Those kinds of things are like, it's not really clear. You'd have to spend a lot of time doing that by hand. And so machine learning, again, the complex nature of that was a huge win. weather as well. A lot of weather algorithms today are actually based on machine learning, and it's because like weather is so stochastic that if you just come up with rules that like you can apply everywhere, this is rather difficult. So leveraging machine learning is a solution to that problem of scale. And also, of course, economies of scale, chatbots cheaper than employing humans, same with self-driving vehicles, handwriting recognition. The MNIST data set that people use a lot in machine learning, that's where you have the individual digits, hand-drawn digits, and you're trying to get the machine to tell which digits represent which numbers. That was started by MNIST, and it's used by USPS for handwriting recognition, or at least it was when they first built the data set. And I had just had to add this last one. We're already so deeply invested in machine learning that our marginal cost to put machine learning and random things is pretty low. So all the AI features that Google's putting into Android kind of fits in that category to me. I also wanted to mention that using other people's work is super valuable. So we know this, of course, as developers because every day we're using other people's software to build our own software. We're building on what other people have done. In machine learning, this is just as important. If you have to write all your own things yourself, not only do you have to write it, but then you have to like figure out if it actually works with your data. And if you can leverage other people's work, that really helps. Software engineering versus data science. So data science, there's a reason why it's called that. It's again, just not, if you've picked a thing, like you've chosen, okay, TensorFlow is going to be my framework for doing this. That's gotten you like that far along the path of getting a working machine learning system. Whereas if you pick up like my front-end framework, I'm going to use Angular, and I'm going to use Node, and you run with that, that's a relatively much larger part of the overall solution. So I also wanted to cover a few concepts that are relevant to the demos. So first, in natural language, I wanted to compare bag of words representation to latent spaces. So not all of the older methods in natural language were bag of words, but this is kind of an example of sort of the spirit of many of the approaches. So a bag of words model will take like an input sentence or sentences, and it'll count the instances of each word in the inputs. So in this case, the first sentence, John likes to watch movies, Mary likes movies too. If each one of these words is a particular location in the array, then the number is the number of times it appears in the input. So the first one's probably John, so we only have one instance of John in the sentence. We have two instances of likes, so that's 2, and so on and so forth. And if we do that for all of our input sentences, we can do comparisons on the arrays that result. And this works okay as long as your sentences have a lot of overlap in the exact words that they use. So it's relying on the fact that we have likes appearing in the second sentence and the first one. If they used a different word that means the same thing, then the bag of words model completely falls over. So it's relying on overlap in the exact words. Also, sometimes the casing if you haven't taken that into account. A more recent approach, like as of like 5 years really, so it's not super new, but like this is sort of the underpinning of a lot of deep learning algorithms, a lot of machine learning algorithms, is the idea that if we try to find a latent space, is what it's called, that represents our inputs, then we can capture more of the semantics of the data. So a latent space is, you can think of it like compression. So you take an input and you compress it down to a representation that is not the same as the input. It's smaller and it's numeric, so you can do processing on it with machine learning algorithms. You're trying to find something that represents that sentence or image or whatever your input is. So an example of that is down here. This is from the, well, this on the right is from the paper on the universal sentence encoder that I mentioned earlier. So the idea is that you take your sentences and then you have an embedding that is essentially an algorithm that finds a latent space. So it's something, the outputs look like this still in the sense that they're arrays of numbers. But these aren't representing like counts of individual words. In fact, we don't usually know what each one of these numbers actually represents, but it's some kind of aspect of the input. So if you have like a similar number for the first item in the arrays, then you would expect that these are similar in that whatever that's representing, that first entry in the array. So you end up getting these outputs. The idea here with latent space is that generally you would have the same length for all of your vectors. So it's not going to depend on exactly like how many different words that you used in your input. Now you have a consistent length. So the universal sentence encoder I mentioned earlier is trained to produce arrays that have 512 items in them. So 512 dimensions in the embedding. And so once you do that, you can apply this, you can apply other kinds of machine learning algorithms that work on input vectors and use these to represent the sentences. So in this case, there's a similarity score that's assigned to these vectors or arrays using just their values. And we can see that there's a sentence, how old are you, which is the first row and the first column. What is your age, the second row and column. And these two sentences are now very similar. So the red values are close to 1, and the light values are close to 0. So we can see that how old are you and what is your age are now considered very similar, even though they don't have any overlap in the exact words they use. But then if you compare how old are you to my phone is good or your cell phone looks great, these are very dissimilar. So the latent space representation is actually capturing the semantic meaning of the sentence rather than the exact way that the person expressed the meaning. Okay. In terms of imaging, this is relevant for the mobile nets example. These different kinds of imaging deep learning algorithms, almost all of them rely on convolutional neural networks. As I mentioned earlier, it's based on convolution, which is this mathematical phenomenon where if you have essentially two different vectors, like an input vector and one that you're applying to it. If you move that vector across the input one and you multiply each item together and you add them, that's what a convolution is in one dimension. If you extend that idea to multiple dimensions, then you get like a more general convolution. So in the case of images, you'll have generally 3 channels for the different colors, red, green, and blue. And so you can represent an image as an n by n by 3 matrix. And then your convolutional neural network will have these convolution layers where they have essentially 3-dimensional tensors, which would be a matrix in our case. If you slide this across the input and you do the convolution on each pixel location, so in this case it's starting here, for the next pixel it will move 1 to the right, and so on and so forth. It's pointwise multiplying each one of these pixels together with the tensor that we're using for the convolution. And the result of one of these convolutions is a single output in this type of convolution. And so you do this across the whole image, row by row, column by column, you end up getting another matrix, in this case a one-dimensional matrix, or like a two-dimensional matrix that's now, the third dimension has been reduced to 1. And if you also notice that because this is a width of 3 and a height of 3, we will get 2 fewer pixels in each dimension, so n minus 2, n minus 2 in the output. And so if you stack these together, so you have an input, you have your input image, and then you have your first layer. If you have multiple layers, you have what looks like this. And so if you've been following deep learning, you've probably seen like tons of images like this. This is a particular architecture for images called VGG. This came out, I don't know, like 5 years ago or something now. But pretty much all imaging networks look like this in the sense that they're generally a whole bunch of layers. And so these black ones are convolutions like I've described here. Then there's generally like some layers between like every so many of them just to reduce the dimensions. So the idea is that we're going from an entire image and trying to reduce it to a single classification at the end. And so that's what's happening here. By the end, we have a vector that has 100 numbers in it, so an array of 100 numbers. And then we can do traditional classification on that. And this is, again, this is VGG, so it's not the exact architecture for mobile nets, but it's generally like the layout. You start with an image, and then you're reducing it to a single vector. And so the last concept I wanted to cover briefly was K-nearest neighbors. This is a classical machine learning machine learning algorithm for classifying data. The idea is that you have a number which is called K, and you look for the K nearest data points in your data set to any point that you're trying to classify. So if I had a point here, and I was trying to classify what color it should be, I find its nearest neighbor, in this case, since K is 1. And in this case, it will be a blue dot, so that would be a blue, classify that as a blue data point. And so the colors here in the background are showing if you had a data point in that region, what would it be classified as? And so in the case of K equals 1, you get a mapping that looks like this. And again, this is 2 dimensions, so you have like one quantity here and one quantity here, but you can do this for higher dimensions as well. Although K-nearest neighbors does break down if your dimensions get too high. But in general, since we reduce our dimensionality down in many different machine learning methods, we can apply K-nearest neighbors to very many machine learning like approaches. And so this is another example, but for K equals 5. And so you're looking for the 5 nearest neighbors, and you're going to assign a label to the point based on whether most of these were the same color. So in this case, we can have ties. So the white regions are where there's no winner among the 5 nearest points. And usually you'll have some kind of approach to break the tie. So this is K-nearest neighbors. Now I will show the demos. So I'll go ahead and bring these up in the code. For the demos here, I used TensorFlow.js with Angular and Node. So my first example, I pulled the latest 25 posts, the titles of the latest 25 posts from different subreddits over the weekend. And then I trained the universal sentence encoder that's you can get for TensorFlow.js. And then I used K-nearest neighbors to classify them to their given subreddits. And so if I give it a new title, it will run the universal sentence encoder on it to get 512 length array. And then it will pass it to the K-nearest neighbors classifier to label it based on those 25 posts from each subreddit that I pulled a few days ago. So if I give it like a title like Windows is terrible, you should not use it. It tells me that it's from the Linux subreddit. Titanfall is awesome. And that's from the gaming subreddit. I can say something like, North Korea launched another rocket. It'll tell me it's from World News. I also made these buttons so that it will pull a random title from the current posts. So if I click on Linux, I get this post, and this isn't in my data set. So it's actually guessing which subreddit it's from just from the sentence. You can get a science subreddit. These ones are pretty good, like World News, Science, Linux. These have like their own like language. Like if you just got one of these titles, you'd be like, oh yeah, that came from that subreddit. Funny can like vary so much that it's not quite as good. So I thought it was videos in this case. Yeah. Wow is funny. Ask Reddit, there's a question mark, so I think it's probably incorporating that in. And so pretty much every tile from Ask Reddit has a question mark, so it's going to be pretty sure it's from Ask Reddit. Same with IAMA, because they always end with that. And today I learned has till. So these ones are kind of cheap, but Linux is cool. World News. I was really surprised about how well this worked. And I think it's all due to the sentence encoder. It seems to be really good at getting the semantics from the sentence. So if I just throw that at KNN with I set k equal to 3, it works really well without me having to do any kind of tuning. So I'll bring up the code for this. I'm actually doing the machine learning stuff on the back end, so there's a Node server that I stood up for this. So I'll pull this up. Yep, this is the subreddit one. So I'll start with a Node server. I just wanted to get this going, so I'm using Express for the API endpoints, and I've brought in TensorFlow. So in this case, I've brought in 3 different pieces of TensorFlow. The top level package for TensorFlow.js. I bring in the sentence encoder and the classifier. And then there's a few wrinkles that seem to be issues that haven't been addressed yet. Maybe they came up with 1.0 that came out last week or something. I have to bring in node fetch for the universal sentence encoder, and I had to do one other thing. Let's see here. Actually, I think that was in the other application I'm thinking of. So once I did that, I was able to use the TensorFlow packages, and then of course I have the Express stuff. And so then I did an async IFI just so I could have async await for all the code. The first thing I do is I get the KNN classifier, so this will create a classifier object for me. And then I also load the universal sentence encoder, and this is an async method, so I'm using await to get it. Once I do that, I add all of the titles from the subreddits to the classifier. So one of the drawbacks of KNN is that you have to have your whole training data set passed into the classifier whenever you want to use it. So in this case, I'm passing in all of the titles that I pulled over the weekend, which I've stored encoded in a JSON file. That's because the USE, the Universal Sentence Encoder, is actually quite slow. Like it took quite a bit of time to convert 25 titles from like 10 subreddits or something. So I just save that so that anytime I start my server, it'll start instantly. And I am passing this into the classifier. In my data set, it's just stored as arrays. And in TensorFlow, we're working on tensors. So I'm just converting it to a tensor here, one-dimensional tensor. And I also pass in the label for that example. So in that case, that's the name of the subreddit. And so once I've added all my examples to the classifier, then I just start my server, port 300 or port 3000 is like the default, so I'm using that. I'm using cores because my server is on 4200, and then I'm using body parsers so that I can use JSON objects. And so once I do that, I can make an endpoint. So if I post to the server at the root, the body will have the title that I'm trying to guess. And so I have that in a value property on the body. And I'm calling model.embed. This is going to use the universal sentence encoder. And of course, that takes time, so it's an async function. So I'm awaiting it. And once I do that, I have my array. I think in this case it's a tensor, actually. Yeah, tensor. And this will be a one-dimensional. So it thinks it's 2 dimensions, but one of the dimensions length is 1. And so if I pass that into my classifier with the, let's see. Not sure what the 3 is. If I predict the class, oh, it's the K, yeah. So it's the KNearest Neighbors. It's looking for the 3 nearest neighbors for this encoded sentence. And it will give me the result of that. And again, this is an async function, so I'm using await. Then I can just respond to my Angular application with the JSON. So in this case, it gives me this object where its best guess is the class index, and then it actually gives me confidences for all the other classes if I wanted to use them. I'm not using them in this case, but if you needed that, you could have it. And so once I do that, I also built an Angular application for the front end. So I have an application here that's just one component, since it's pretty simple. I have my labels. I could have made an endpoint to get it from the back end, but I just hard-coded it here. And then I have my control for the title that I'm typing in. And then I have some plumbing, so I have a subject for the predicted value. It's also for string, like for the state of the prediction, essentially, that the template will use. And then I have a subject for the title to post. This was just making it easier to use observables to do everything. And so in my constructor, I'm looking at the value changes on the control. So anytime I type something in, I'm doing some like not so great things with the subjects just for expediency. So here I'm actually clearing the predicted with a tap. Then I'm debouncing this so that it's waiting for the user to stop typing for 1 second. I'm filtering out invalid values. So I think because I'm using, not sure why I have valid on here, but apparently I'm filtering out, I think I thought I was going to use an async validator and ended up not using one. So it filters out any invalid values, which I don't think there will be any. And then it puts the result of this into my subject for the titles. And so then I use my title subject. I only do this processing if the text changed. So if I didn't actually change the text, it won't do it again. And I switch map to an HTTP post. I do a switch map so that if I start typing again, it'll cancel the HTTP request. It starts off with the loading state. So my template picks up on this and changes what it shows based on that. I do a post to the back end with the value passed in. So the value is the string for the title. At this point, I'm just console logging. Then I map to get just the class index. So as I mentioned, it gives you confidences as well, but I'm throwing that away because I don't need it. I'm just getting the best guess. And then I have some error handling. And so the result of this is put into the predicted subject. And that is used in the template. And I also have a method for the buttons. So to get a random title from one of the subreddits, it will clear the prediction, essentially telling the template that I am in the process of loading a new one. I do a GET request to the Reddit API to get JSON for the latest 25 posts. I'm actually grabbing the title from them, and I'm getting a random one from the JSON. So if I switch to the templates, I have my input box for the title and an error message. I guess it's because I have it set to be required, I guess. Maybe. And I have my predicted value, which is this middle text. I'm using an H1 for that. And I have some cases here, so it's looking for the loading state to show that progress bar. And when it's not loading, if it's been loaded but it hasn't gotten a prediction yet, it'll have that initial message to enter a title. Otherwise, it will show the actual prediction. And since that's an observable, I'm using the async pipe, so I'm not having to do any special handling of the observable. And then I have my buttons at the bottom. So I'm doing an ng4 over all of the subreddits, and when I click one of them, it calls that method with the subreddit name. So I'm using Angular material for all of this, so that's where all this stuff comes from. Makes it really easy to make a nice looking layout. So then I have one more example. The second example is using mobile nets. So I'm going with the idea of automatically labeling pictures that users have uploaded. And in this example, I'm doing everything in the front end. So there's no node server, it's all in the browser. Oh, going over time. Okay, so let's show it. So it's automatically labeling different things here. It doesn't work so well sometimes if you get something unusual like snow, but it's correctly picking out people. These are jellyfish, so this is nature. We have water, nature. These are not labels coming from mobile nets. I labeled a whole bunch of images in a different set, and then I'm using KNN. So I'm using mobile nets to get that latent space vector, and then I'm using KNN to classify them based on my classes. So behind the scenes, mobile nets is not classifying almost any of these images correctly. It gives me like a list of like incorrect predictions for what they should be. But I'm using that because they're going to be consistent. Like it's going to consistently be wrong about what water looks like in like some random picture of an ocean looks like. I'm using the fact that that's pretty consistent to classify them. So, and again, this is Angular material for the look and feel. And I'll leave the component up here. So I'm just using the MobileNet package, and I'm looking at the wrong thing. This is the application. So I'm bringing in the 3 different pieces I need from TensorFlow, and then I have my classifying the images part. So.
Is your code available online?
It's on GitHub, but I need to like flip the switch to make them public, so it will be, yeah.
Can you post that on the YouTube video, or where would you go link to that?
Yeah, I can definitely do that. Yeah, we'll try to put that in the YouTube video description. So.
Make sure you include your social security number.
Yep. All right. Well, thank you very much.